This two-part course is designed to acquaint new and incumbent theater employees with the theory and care of theater motion picture equipment. Specific topics to be addressed are film inspection and splicing, projector head theory of operation and component cleaning, sound head theory of operation and component cleaning, theory of operation and maintenance of the carbon arc lamp house, theory and operation and care of projection lenses, and the proper techniques for threading the film in the projector. Automation in modern theaters has presented a number of problems to the projectionist. The two most important of these being the correct identification of the film's title and the correct part number of a given reel. These problems begin when the film is to be shown on large reels such as these. Showing the film on this type of automated equipment requires the removal of the leaders and tails and splicing together the standard 20-minute reels used for shipping to produce a continuous performance on a single projector. To overcome these identification problems, most commercial projectionists are now leaving a few frames of picture on the leader and tail of each reel. This procedure will allow for proper visual match of the leaders and tails to their corresponding film rolls when the film is being reassembled and readied for transit to the next theater. The art of visual and touch inspection will be your most difficult job to master. You'll need to develop an ability to consistently locate film damage. The inspection the film will receive here will determine the enjoyment level of the patrons who will view the feature this evening. Touch inspection consists of holding the film edges between the thumb and first finger and applying enough pressure to cause a curve in the film with one hand while turning the hand rewinder slowly with the other. Excessive film speed will cause friction and heat on your fingertips. Keep the film speed down to ensure good inspection. You should never touch the body of the film during inspection because it may deface the image. Never use a rag or tissue to clean an oily print, as the debris that becomes lodged between the soft, dull film emulsion and the rag will always scratch the print. Occasionally, you may find what is known as split sprocket holes. This particular type of film damage requires special preparation before the film can be shown. Repairing this type of defect involves the cutting of a V shape on the outside edge of the film, entering into each damaged sprocket hole, thus forming a notch. This notching process will prevent the leading edge of the split from catching and tearing in the projector mechanism during the performance. Should you be faced with multiple splits over a small area of film, you would be well advised to splice out the affected area. Historically, the most commonly used splice in the industry has been the overlap cement type. As the description implies, the two ends of the film are joined together by overlapping, then they're bonded by a suitable film cement. The most common cement splice used in theaters and film exchanges is made on a benchtop splicer, which is designed to include a sprocket hole in the overlapped area. The area of overlap maintains the 4 sprocket holes per frame on either side of the splice, which is required if the film is to stay in frame when projected. A satisfactory splice demands careful scraping to make sure all the emulsion, binder, and any foreign substances are completely removed. The surface on the film to be joined must also be thoroughly cleaned. If the base surface contains even a slight film of oil, some difficulty may be encountered in obtaining a successful splice. Very often this factor is overlooked, and poor splices are falsely attributed to the particular cement used, to the splicing equipment, or to the film base itself. Sometimes it may be helpful to roughen the base surface slightly when films resist satisfactory splicing. An easier, more effective technique of ensuring a good splice is to apply a very small amount of cement to the base side of the film to be joined, then wipe it off immediately. This initial application of cement acts as a primer coating preliminary to the actual splicing operation, and it aids in obtaining thorough adhesion of the two surfaces. The most common mistakes made while preparing a film for splicing are not removing all of the emulsion from the film base prior to applying the film cement and gouging of the film base with the scraper, which weakens the area of the splice. When the emulsion and binder have been satisfactorily removed, the cement should be applied to the splice area. Enough cement should be used to wet the scraped area, but not so much that it will run outside the splice when the two sections of film are pressed together.
It's important to allow a holding time of at least 1 minute under the uniform pressure created by the splicer clamps.
At the end of the bonding time, the pressure may be released and the finished splice rubbed with a soft cloth held over the finger to help seal the cut ends. It should be emphasized that it is important to bring the two surfaces under pressure as quickly as possible after application of the cement. After a sufficient holding time, the splice may be tested by gently flexing the film. Because a cement splice does not usually attain full strength for several hours, care should be exercised when handling the film if immediate use is contemplated. A well-made splice should not contain any bubbles or hazy areas that indicate an imperfect weld. As you may have guessed by now, splicing is indeed an art that requires practice.
In review, you should always observe the 1 minute drying time of the film cement. Insufficient holding time in the splicer is the prime cause of early weld failure. Never mix old and new film cement, and always keep the cap on the cement bottle tightly closed to prevent the solvent from evaporating. Check the film stock to be joined for cleanliness and keep the splicer clean and free of debris.
Over the past few years, the growing popularity of automated projection systems and more recently, the limited availability of polyester-based films has influenced the emergence of the tape splice. This is a splice in which the film ends are securely fastened together by a very thin, perforated polyester tape with pressure-sensitive adhesive. Although commonly used for many years in the 8mm and 16mm field, the tape splice for 35mm applications was not seriously considered before. The need for multiple splices and the loss of picture frames when making regular overlap cement splices have motivated the popularity of tape splicing.
Tape splicing is accomplished by butting the edges together of the two film ends to be joined. The positioning pins and the cutting bar of the splicers used in exchange theaters are designed to correctly orient the film for a butt tape splice. Each tape splice should be of sufficient strength to prevent it from hinging or collapsing when the splice is flexed.
Once you have cut the film ends at the proper place for an end-step splice, the tape splice can then be applied. The tape should be positioned so its center approximates the center area of the splice and then press it into position. When using the mylar tape method, both sides of the film should be taped to prevent the leading edge of the splice from catching in the projector mechanism and possibly tearing the film, causing an interruption in the performance. After completing the splice, be sure that the soundtrack continues on the same side of the film on both sides of the splice.
Misaligned film edges at the splice joint can sometimes occur. This defect is usually caused by worn splicer components or poor preparation and can only be corrected by remaking the splice.
Using this technique will help stabilize the splice and eliminate possible picture jump as the splice passes through the projector. After the inspection of each reel of film has been accomplished, place it in the electric film rewinder and rewind it back to the beginning. Note the placement of the reels and the direction of film travel. After rewinding, the film should always be stored in appropriate containers while in the projection room. The next area to be discussed is changeover cues. The cue is probably the most single important visual tool to be used by the projectionist to create a smooth performance. Your understanding of their correct placement and use will add markedly to your showmanship abilities and the presentation of a smooth performance.
Timing cues appear at 11 feet and 1 1/2 feet before the end of each reel and are used to obtain the required continuity in the presentation during projector changeover.
The cue marks appear in the upper right-hand corner of the film as you view the picture image as it's seen on the screen. In most cases, cues are put on by a film laboratory and normally appear as a black dot or a black dot with a gold crown surrounding it. But on the older films, you may find the standard scratch cue that has been placed there by a film inspection service or a commercial theater projectionist. In no case should you add your own cue marks or change the existing cues unless necessary for a smooth performance. If there are no cues present, use the grease pencil that's been supplied to you.
Both the startup and changeover cue appear in 4 consecutive frames. Each set has a total viewing time of 1/6 of a second. The cue set that appears at 11 feet before the end of each reel signals the startup of the incoming machine. The cue set that appears 1 1/2 feet before the end of the picture signals the changeover of light and sound from the outgoing projector to the incoming machine.
If existing cues are incorrectly spaced, or if multiple cues are present and detract from the picture content, splice them out during the inspection process and insert the proper cues. This will lessen the confusion for the proper timing of changeovers for yourself and your fellow projectionists, and will remove the visual disturbance for the patron. Again, remember, always use the grease pencil for inserting in-house cue marks. Many theater patrons believe the image on the film moves, when actually there's no such thing as a moving picture. Movies are nothing more than still pictures of closely related action, printed on a long, narrow strip of film and shown one picture at a time in such rapid succession that the image appears as one moving picture. The 2 principal parts of a motion picture projector used to accomplish these rapid successions of pictures are the intermittent mechanism and the shutter. The intermittent mechanism consists of 2 major components. They are the star shaft and its actuating cam. The star is engaged for a quarter turn during each full revolution of the actuating cam. The quarter turn of the star pulls down the film 1 complete frame each time it is actuated. The 2-segment shutter, which is placed between the light source and the film aperture, is synchronized by gears to the intermittent movement. The action of these components cuts off the light beam at precise intervals while the film is being moved downward, and again while the film is being held stationary in the projector. The first segment of the shutter that interrupts the light beam while the film is in motion is known as the pull-down blade, and the second is called the anti-flicker blade. With the action of the intermittent movement, the film is advanced and positioned in front of the picture aperture. Each frame of film is held for an instant in front of the aperture and then pulled away very rapidly. This sequence proceeds at the rate of 24 frames per second. This does not imply that each frame is held on the screen 1/24th of a second. The actual time is about 1/2 of this, where the screen is darkened twice, once while the film is moving downward and again while the picture is being held stationary in front of the light source. 2 loops of film are used, one above and one below the picture channel. Without these loops, the film would not pass the picture aperture intermittently. Also, the lower loop of film must be exactly the right size for proper synchronization of the sound and picture.
The soundtrack signal leads the projected image by 20 frames.
The complete projection system is comprised of 4 distinct parts. They are: 1, the projector mechanism, usually referred to as the projector head; 2, the arc lamp, usually called the lamp house; 3, the sound reproducer, usually referred to as the sound head; and 4, the optical train, which consists of the lenses required to project the picture image. The care and cleaning you give this equipment will be the determining factor in the quality of the presentation. Clean equipment is the cornerstone of good showmanship. The good housekeeping of the projection room and the overall cleanliness of the equipment is a good indicator of the abilities and attitudes of the projectionist staff. We are now going to give you some of the basic operating theory of each of these major components and the maintenance that each is to receive during the servicing period of your workday. In the projector mechanism, the first area to be cleaned is the film trap and door. The door is removed by first moving it to the open position by means of the spring-loaded release lever. When the door reaches the fully open position, the release lever catch will hold it in place. With the door in the open and locked position, it can now be removed by unscrewing the 2 knurled pressure nuts that hold it in the position and then pulling it outward. The film door consists of three distinct operating parts. They are 1. The upper pressure pad, 2. The lower pressure pad, and 3. The intermittent pad shoe. The film tension adjustment is used to control picture jump and weave that may occur on the screen due to excessive sprocket hole wear in the print or the accumulation of lubricating wax or other debris in the area of the film trap. The intermittent pad shoe controls the film as it enters and leaves the area of the intermittent sprocket. The upper and lower pressure pads stabilize the film in the picture channel when it is moving and at rest. All film door components should be thoroughly cleaned of dirt and wax buildup that accumulates during projection by using a stiff bristled toothbrush. In no case should any component be cleaned with the equipment running. With the film door clear, the trap can now be removed by loosening the threaded holding pin that holds the trap in place. When the threaded holding pin clears the projector mainframe, it can be removed by pulling it outward. The trap should also be thoroughly cleaned of all debris. Failure to do so may result in screen image unsteadiness during projection. Care must be taken to ensure that the 90-degree angles where the film guides meet the film shoes are thoroughly cleaned. This is the area most overlooked during cleaning and has the most effect on picture steadiness. The lateral guide should also be checked during the cleaning process. Both guides should spin freely, and the guide on the left, as seen from the rear of the trap assembly, should float freely on its supporting shaft. This horizontal floating action allows the guides to accommodate splices and varying film widths.
If the action of the guides appears sluggish, add a small drop of oil to each of the two shaft pivots. Whoops, too much. If oiling does not free the action, call for service. Do not attempt to repair the problem yourself, as special tools are required to ensure proper component alignment.
With the film trap components removed, the intermittent sprocket assembly can now be cleaned. Because of its relatively high speed of operation, this area is most likely to suffer from severe accumulation of film debris. This fact, combined with its difficult access for cleaning purposes, makes it the most often neglected point in the mechanism. Demonstrated here are the proper materials and techniques for getting the job done. Note the use of the toothbrush and Q-tips. The sprocket position can be changed by using the motor shaft knob located on the front of the sound head. Turning the framing adjustment will change the overall position of the intermittent assembly, making those hard-to-get-at places more accessible. The area of the intermittent sprocket should be thoroughly cleaned prior to every performance. With the film trap components clean, it is now time to install them in the projector. As with most things mechanical, it is often easier to remove a given component than it is to replace it. This is especially true of the film trap. The trap is provided with two alignment holes. The alignment holes on the trap mate with their corresponding pins on the mechanism. This mating effect guarantees alignment. The major working component of the film trap area is the fire shutter. Your understanding of its operation is not only important for the correct reinsertion of the film trap, but for the overall safe operation of the projection equipment. When the equipment starts, the fire shutter normally raises clear of the arc light beam. Should the film break above the aperture, it automatically drops into position, activated by the trigger wire. When rethreading following a film break, the fire shutter must be reset by depressing the reset button located on the top left rear of the projector mechanism. For correct alignment and operation of the fire shutter, it is necessary to raise the fire shutter clear of its rest pin located on the base of the film trap by using its reset button. Failure to raise the fire shutter prior to film trap insertion will result in it being jammed in the closed position, preventing it from raising clear of the arc light beam when the projector is started. With the fire shutter clear of the operating area, you will find that the dowel pin alignment holes discussed earlier make for an easy installation. Avoid over-tightening of the holding pin because the heating and cooling of the metal surrounding the threads may make its next removal difficult and in extreme cases almost impossible. With the trap in place, the film door can now be reinstalled. The next areas to be cleaned are the sprocket and pad roller assemblies. As in the case of the film trap, this is one of the few places where the film actually makes contact with the mechanism. It is vitally important to keep all of these areas as free of debris as possible.
To clean the sprockets, slowly move them by turning the sound head motor knob while using a stiff bristled toothbrush.
The pad roller, which guides the film around the sprocket, is probably the most difficult component to clean. This is due to its shape, color, and relatively inaccessible position which it occupies within the projector mechanism. This single component is responsible for at least 25% of all print scratches and is caused by debris buildup which has gone undetected by the projectionist. All sprocket and pad roller assemblies should be thoroughly cleaned prior to each performance and more often if needed. Proper lubrication of the projection equipment is vital. High-cost components such as the intermittent movement can be severely damaged for the lack of a few cents worth of oil. Projector head oil levels should be checked daily. The best indicator of sufficient oil in the reservoir is when a full oil stream is seen flowing from the intermittent oil supply tube after the machine has been running for a few minutes. If the flow is intermittent or if bubbles are seen, the oil level is insufficient and new oil should be added. Use only oil that has been clearly marked for use in the projector head. The use of an incorrect oil will damage the mechanism. The next area to be addressed is the care and cleaning of the sound head. Sound is recorded on film as a continuous photographic image along a narrow strip at one side of the film. The narrow strip is called the sound track. There are two types of sound recording impressions recorded on film. Sawtooth or zigzag waves denote a variable area recording, whereas parallel bands varying in space and intensity along the length of the film denote a variable density recording. Unlike the picture, which is produced as a series of images, the sound is recorded and reproduced when the film is traveling at a constant rate of speed. The sound wave images are recorded on the soundtrack in such a way that the beam of light passing through the soundtrack will vary as it falls on the solar cell. As this light beam varies, the electrical impulses produced by the solar cell also vary, and it is these impulses built up by the amplifier that are changed into actual sound waves by the loudspeaker. The greater the width of the sound waves on the film, or greater the density of the soundtrack bands, the greater will be the variations in the amount of light reaching the solar cell. The recorded soundtrack determines both the variation in the intensity of the light transmitted to the solar cell and also the rapidity with which these variations of light intensity occur. The variations of light intensity control the volume of electrical impulses to the amplifier. The rapidity of change gives the pitch and tone and thus creates sound, music, or speech. The ability of the projector to reproduce musical pitch is dependent upon the absolute smooth and constant rate of film travel past the point at which the photograph soundtrack is converted back into electrical modulations. A mechanical means, usually a flywheel, is provided for changing the intermittent motion of the film to the steady motion which is necessary for good sound reproduction. The components required to energize and detect these film recordings are 1. The exciter lamp. 2. The lens assembly, which focuses the image of the exciter lamp filament onto the surface of the film soundtrack. And 3. The solar cell, which converts the light impulses into small electrical currents. This illustration shows a cross-section of the operating components to be found in most sound optical trains. The exciter lamp is powered by a direct current source, usually referred to as the exciter supply. A portion of the light generated is captured by the first lens group and focused on a device known as the lens slit, which is similar to the projector aperture plate. The servicing technician, during the alignment procedure, will adjust the relative vertical position of the exciter lamp filament so that it aligns with the exact center of the slit, allowing the maximum amount of light possible to pass through. The slit then shapes the light into the identical light pattern that was used to record the original sound image. The second group of elements focuses the light pattern of the slit onto the surface of the film. The need for good optical alignment is critical for good theater sound. Tolerances below 1/1000th of an inch are common in most sound reproducers. As you may have decided by now, the cleanliness of the sound optical train and its associated components is essential for good theater sound. To properly clean the sound head optical train, use a Q-tip in the moisture of your breath. Clean both the front and rear of the sound lens thoroughly. Then clean the face of the solar cell. Remove the exciter base and wipe the glass surface of the exciter lamp clean, as it is made of crystal and its clarity contributes to the overall performance of the system. With the sound optics clean, the cleanliness and mechanical operation of the sound gate should now be checked. This device guarantees alignment of the film soundtrack with the sound optics. The functioning areas of the sound gate consist of 3 parts. They are 1, the interior film guide, 2, the exterior film guide, and 3, the pad roller. The film guides control the film edges and maintain proper alignment between the film and sound optics. The interior guide floats on its supporting shaft against a small tension spring, which allows the assembly to accommodate varying film widths and splices with minimal disturbance to the soundtrack alignment. The controlling surfaces of both guides should be thoroughly checked for proper mechanical action and cleaned of debris on a daily basis. Never add oil to the lateral guide shaft if its action appears sluggish. The pressure roller assures film tension around the sound drum. This component is needed to stabilize the film speed past the sound optics and should roll freely. The next area to be discussed is the projection light source. Since the majority of AFI's theaters use the carbon arc as a light source, we'll concentrate our area of study to this method of producing the high-intensity light needed for projecting a motion picture. The occupation of motion picture projectionist began when a light source was coupled to a projector. For an audience of many people, the first movies were illuminated by a flame fed by a block of calcite, similar to the modern substance known as carbide. This method had a short life and soon gave way to the carbon arc, which is now stepping aside for the xenon lamp, an arc surrounded by a special atmosphere contained inside a quartz envelope. Now the most powerful light to pass through the eye of a needle, the projector aperture. Motion picture projection would never have reached and could not maintain its present high place without the aid of the carbon arc or xenon light source. The increasingly larger screens, long projection throws, and demand for higher levels of screen illumination in both indoor and drive-in theaters, where screens may be 150 feet wide or even larger, require an intensity in the light source that only the carbon arc or xenon lamp can supply. The brightness of the positive carbon crater or xenon anode may be as much as 7 million times the brilliancy of the screen. The high-intensity carbon arc is such a commonplace and generally useful light source in projection applications that little thought is ordinarily given to the physical processes involved in the operation of such a source. Since a temperature of approximately 2,800 degrees is sufficient to produce a white heat, some of the brightness of the carbon can be attributed to particles of incandescent carbon giving off light energy in the area of the arc crater. Due to these extreme operating temperatures, the arc lamp requires the highest degree of recurring maintenance. The brightness of the high-intensity arc is the result of a combination of high concentrations of electrons in the arc stream combined with an atmosphere of flame materials volatilized from the special coring of the positive carbon. These flame materials are in most cases compounds of the cerium group of rare earth metals that are combined in a mixture with carbon in the core. As the carbon burns, forming a crater, the core is exposed to the extreme arc temperature and is vaporized into the crater enclosure. Part of the core material leaves the crater floor as a gas, while the rest is released in the form of small particles of molten core material.
The rare earth atoms in the gas are bombarded by electrons to produce very intense light. It may be helpful here to picture a hailstorm in the positive crater with many billions of rare earth atoms continually colliding with each other and with electrons. As the result of such collisions, a rare earth atom absorbs energy and is transformed into an excited state generating light. All the brightest portion of the gas ball cannot be focused on the film plane unless the crater of the positive carbon aligns exactly with the optical axis of the mirror, which is in alignment with the center of the aperture. When misalignment occurs, the plane in focus will include either shell light, which is of a lower order of intensity and more yellow, or arc stream light, which is also of lower intensity and more blue. The image of the gas ball must fall precisely on the film plane if a maximum amount of light is to pass through the rest of the optical system. Finally, the optical axis of the projection lens must be exactly along the axis of the mirror and aperture, thus permitting maximum light transmission. The alignment of both the positive and negative carbons can be seen on the arc imager card. The carbons should be aligned so they sit in the indicated position during operation. If all elements are operating correctly, you'll get the best light on the screen. The carbon arc lamp consists of 7 operating components. They are 1. The arc feed motor, which feeds the carbon rods into the area of the arc as they are consumed. 2. The reflector and its associated assembly and adjustment controls. 3. The negative carbon advance assembly, which advances the negative carbon into the area of the arc and provides the negative electrical connection to the carbon rod. 4. The positive carbon advance assembly, usually referred to as the positive tray. This component provides the electrical connection to the positive carbon rod and provides the mechanics to advance the carbon into the area of the arc during operation. 5. The positive drive, which powers both the positive tray and the negative carbon advance assembly. 6. The hand dowser assembly that protects the mirror and the projector head from the intense heat rays of the arc when the projector is at rest. And 7. The power supply, which is no more than a low-power direct current arc welder. As you may have experienced, depending on your tenure as an AAFES projectionist, it's not any fun to have to hand-feed a carbon arc lamp house during the presentation of a feature. By and large, the bulk of the mechanical failures of the lamp house can be attributed to the neglect of the arc feed motor. One of the most common abuses the arc feed motor receives occurs when the well-meaning but uninformed projectionist over-oils it. Most projectionists have difficulty gauging the amount of oil required for effective lubrication. And all too often, when more than one projectionist works at a given theater, the motor is deluged with multiple over-oilings, which instead of improving its operation, is the primary cause of its premature failure. To overcome this type of failure, 2 things must be done. First, one member of the projectionist staff must be appointed to perform all routine lubrication. Hopefully, this will end the multiple over-oilings of the motor. Second, a lubrication chart showing the planned dates for oiling each component should be made by the individual responsible and posted in the projection room for use by the other projectionists when required. Once a month, the arc motor should be removed from its supporting casting and the carbon brushes and their holders inspected. With the brush cap removed, the brush tension spring will then be exposed. A gentle outward tug on the spring will tell the story. If the action of the brush in the holder is smooth, you're in good shape. If not, maintenance of the motor is in order. Servicing consists of removing the brushes and cleaning the interior of both brush holders using a cotton swab saturated with alcohol. Repeat this process until a clean swab tip is obtained. If the action of the brush in its holder is sluggish, you have the beginnings of a premature failure, and the motor will have to be disassembled for a thorough cleaning. To clean the motor, first disconnect the 3 electrical connections in the area of the fuse block. These wires are color-coded, and a diagram of their proper connecting points is usually located on the fuse block cover. After removing the brushes, Unscrew the 4 bolts that are located in each of the bell housings to expose the interior of the motor. Here you can see the magnitude of the over-oiling problem. As the motor runs, the excess oil leaks from the area of the bearing down the armature shaft and is thrown throughout the interior of the motor, including the exposed ends of the carbon brushes. The oil then mixes with the carbon dust that is always present and forms a sticky sludge, which eventually jams the brush in its holder and causes it to lose electrical connection with the commutator surface. When this electrical connection is lost, the motor stops and your problems begin. The motor interior should be cleaned with a suitable solvent such as type cleaner. Avoid stressing the electrical connections to the brush holders.
With the cleaning process complete, add 1 drop of projector oil to the bell house bearing.
The commutator should be cleaned with a pencil eraser until a uniformed copper color is obtained throughout. Be sure to clean away any debris left by the eraser at the end of this procedure. The motor can now be reassembled. Confirm the free spin of the armature before and after the tightening of the bell housing bolts. This method will avoid binding of the armature shaft caused by incorrect alignment of either bell housing. Worn, cracked, or broken brushes should be replaced. Brush replacement should always be done in pairs. Avoid mixing old and new brushes in the same motor. When installing new brushes, confirm their complete freedom of movement in their holder. Because they're molded, some brushes may need to be lightly sanded with an emery board or fingernail file to obtain a proper fit. When reinstalling the original brush set, make sure they're returned to their original holder and position. This is necessary because of the wear pattern that develops on the face of the brush. To determine the correctness of the brush position, insert the brush into the holder and apply pressure by depressing its tension spring. Rotate the armature in a clockwise direction. If a light buzzing sound is heard, remove the brush, turn it 180 degrees, and reinsert it into the holder. If the position of the brush is correct, the motor will rotate smoothly without creating the buzzing or traveling sound. Repeat this process for both brushes. With the motor reassembled, it can now be remounted on the lamp house. Reconnect the motor wiring to the lamp house interior. If you have any doubts about the placement of the wires, check the diagram or the other lamp house. Some alignment between the shaft of the arc feed motor and the shaft of the worm gear located on the positive drive will have to be made. This alignment is usually accomplished by leaving the motor mounting screws about hand tight. With the lamp operating, gently adjust the motor position until the coupling spring ceases to vibrate. Once proper alignment has been achieved, secure the motor mounting screws. The reflector is the major optical component of the lamp house. It is mounted in a cradle that permits adjustments that become necessary from time to time. The control for the adjustment of the reflector are located on the rear door casting. The lower control adjusts the vertical axis. The upper control adjusts the horizontal axis. The center control is the override feature for the negative feed assembly. The reflector requires vigilant care if it is to maintain its optical properties. Because of the extremes of its working environment, it requires daily cleaning. Use the Bonami cleanser that has been provided. Be sure never to clean the reflector when it is hot. The negative carbon feed assembly is located behind the mirror cradle. It feeds the negative carbon into the area of the arc. This assembly should never be oiled except at the oil ports that have been provided. Adjustments for controlling the vertical and horizontal position of the negative carbon are provided to maintain a flat face on the positive carbon as it burns. The intermittent feeding action of the negative assembly is accomplished through the ratchet mechanism, which is activated by a push rod that runs the length of the lamp house and is driven off a cam located inside the positive drive. The push rod intermittently presses against the ratchet mechanism lever. The thumb screw located at the bottom of the lever provides a means for adjusting the feed rate of the negative carbon. Turning the thumb screw clockwise increases the length of travel of the ratchet arm, which in turn increases the feed rate of the carbon. Turning it counterclockwise shortens the travel of the arm and reduces the feed rate of the negative carbon. The spring-loaded carbon clamp provides the DC electrical connection for the negative carbon and is completely insulated from all other components. The positive carbon feed mechanism, usually referred to as the positive tray, provides the mechanical means for advancing the positive carbon into the area of the arc as it is consumed. Its feed rate is set by the feed rate control, which varies the speed of the arc motor. The positive clamp provides the high current electrical connection to the positive carbon. Fed by a flexible cable, the clamp is totally insulated from all other electrical connections and should never be lubricated. Because of the extremes of operating temperature, oxidation of the positive clamp cable connection is inevitable. For this reason, the quality and tightness of this connection should be checked periodically. The positive carbon rest is the primary adjustment for obtaining the correct optical alignment of the positive carbon. As in many other areas of projection equipment, proper component alignment requires special tools. However, in an emergency, should the rest be damaged during lamp operation, the following procedures will give a good relative alignment of all components. First, remove the set screw holding the damaged rest. Note the position of the 4 dowel pin alignment holes that surround it. When confronted with this task, it may be helpful to draw a small picture of what you see. 2 of these holes mate with corresponding alignment pins located on the main frame casting of the positive tray and preset the vertical position of the rest. Check the edges of the replacement rest for the carbon size imprint, which should be stamped into the metal. These numbers correspond to the 2 positive carbon sizes used in AFIS theaters. When installing the replacement rest, the number of the carbon size used in your theater should be facing you. In cases where the replacement rest does not have an imprinted carbon size, refer to the drawing you made earlier and position the alignment holes of the new rest accordingly. To check the trueness of the rest alignment, first select a straight positive carbon. The straightness of the carbon can usually be confirmed by rolling it on a flat surface. With the positive carbon placed in position, release the positive feed lever and run the assembly through its complete cycle. If the tip of the positive carbon veers from center, further alignment of the rest will be required. For horizontal misalignment, gently tap the rest on either side until the carbon travel is in a straight line throughout the complete operating range of the mechanism. One of the most common symptoms of positive carbon misalignment is the need to continuously adjust the position of the negative holder to maintain a flat face on the positive carbon. When the carbon is out of alignment in the vertical plane, erratic burning patterns like this one develop. Note the position of the positive carbon as it nears the end of its burn. This type of problem usually requires a modification of the positive rest support casting and should be accomplished by the equipment and facilities technician responsible for service at your theater. With carbon alignment achieved, the mirror can now be adjusted as required to obtain a flat light field on the screen by using the respective mirror controls. If you cannot obtain a proper adjustment of the positive carbon or mirror by using the procedures that have been outlined, don't hesitate to call for service. The projection lens is the final step in the delivery of a sharp, clear screen image. As we shall see, it requires constant inspection and the use of proper procedure for its effective care and cleaning. The image-forming property of the lens is a familiar phenomenon. The principles which produce the projected image in the simple projection system are the same principles which operate in cameras, telescopes, binoculars, microscopes, and other optical devices. The projection of a motion picture on a screen is based on the principle of the formation of an image by a convex lens. The simplest type of projection system consists of a light source, an image on a transparent base, and the lens. To focus the projected image, the distance between the picture on the screen and the lens is varied until the sharpest image on the screen is obtained. Adjusting the distance between the picture and the lens for maximum sharpness of the projected image is called focusing, and every commonly used projection system has some convenient mechanical means for making this adjustment. The lenses required for projection come in two sets. The lenses on the left are for the projection of a standard or regular size picture. This lens set, one lens for each projector, is usually referred to as the flat lens. The lens set on the right are for the projection of a cinemascope picture. As you can see, each scope lens comes in two distinct parts. The smaller lens, usually referred to as the prime lens, and the larger lens called the scope attachment, which comes in various shapes and sizes. Each lens is numbered either 1 or 2 and corresponds to the projector in which each is to be used. The need to use a given lens in a specific projector comes from the customizing of the optical train of each machine during the initial setup of the equipment. The prime lens assembly comes in 4 distinct parts. They are: 1, the focusing ring, which ensures that the lens will always be in an in-focus condition when installed. 2, the lens adapter, which modifies the diameter of the lens. 3, the lens shown here with the adapter and shroud removed. And 4, the lens shroud, which protects the rear of the lens from accidental damage and controls the reflected light from the rear element of the lens. Each lens set has a corresponding aperture plate, which, like the lens sets, has been tailored to the projector in which it is to be used. The aperture will determine the final size and shape of the projected image. The aperture plate on the left has a rectangular opened area, and it is for the projection of a standard-sized picture, while the aperture plate on the right has a large, almost square open area and is for the projection of a cinemascope picture. This difference in open area makes for easy identification of each aperture plate type. Each aperture plate should be numbered to agree with its corresponding lens set. The inspection of the lens is a simple procedure. Just hold it up to the light and look through it. If debris is seen, the lens should be cleaned. Clean the lens only when necessary, using the moisture of your breath and the lens tissue that has been provided. Never use your shirt or any other material or liquid that may damage the soft optical coating on the lens surface. A clean porthole glass is also essential for a clean, sharp image. It should be inspected on a daily basis and cleaned as required. We're now going to demonstrate the proper procedures for threading the projector and operating the carbon arc lamp house. Although the methods you adopt may differ slightly, either because of your manual dexterity or personal preferences, the end results should be the same as those to be shown. The first step in threading the projector begins by opening all the film path assemblies. Load the film to be shown in the upper feed magazine. Don't forget to lock the spindle down. Pull the leader of the film roll down to the take-up magazine and wind it around the take-up reel in a clockwise direction. Take care not to let the film touch the floor, as the always present static electricity attracts dirt like a magnet. And once on the film, it is distributed throughout the print during projection. The damage done by this type of debris appears on the screen as very small specks and scratches and is most noticeable by the noise it produces on the soundtrack. The entire threading path of the projector is shown here. To make the threading process as easy as possible, you should first lace the film in its approximate final position within the film path. With this accomplished, final lockdown begins at the film trap by first positioning the intermittent sprocket in the rest or lock position. This condition is indicated when the line on the outer bearing support casting aligns with the line on the sprocket shaft collar. You can position the sprocket at any one of its 4 at-rest positions by turning the sound head motor knob. The film should be positioned in the trap so that the center of the numbered frame on the film aligns with the approximate center of the illuminated framing port. The frame used for framing the film in this procedure, depending on the type of leader, is either a footage or a second countdown number. The numerals 6 and 8 are the most often used settings depending on the type of leader used. The centering of the frame in front of the illuminated port is accomplished by selecting the proper set of sprocket holes that are to engage the intermittent sprocket. One of your final checks of this area will be to confirm that both sides of the film lay flat against the face of the sprocket and that the teeth are properly engaged. With the proper sprocket hole selected, a slight pull on the film in an upward direction will hold the film in place, freeing one hand to close the film trap door. To relieve the pressure on the door catch, move the door to its furthermost open position, depress the release lever, and gently close the door. The upper loop of the film should be of sufficient size to allow for the proper feeding action without touching the film brake trigger wire. Before closing the pad roller assembly, make sure the sprocket holes on either side of the film are properly engaged. The easiest procedure for sizing the loop below the film trap can be accomplished by using the film stripper as a touch point in conjunction with the width of your first finger. As before, make sure that the film is properly seated before closing the pad roller assembly. When threading past the sound drum, the tension of the film around the drum should be lax enough to permit the insertion of your first finger between the film and the bottom portion of the projector mechanism casting. To adjust the film tension around the sound drum, engage the film to its tightest position on the upper sound head sprocket assembly and then back off 2 sprocket holes and close the pad roller. Close the sound gate by pushing the locking knob of the gate forward until it clicks in the locked position. To size the loop above the lower sound head sprocket, normally called the holdback sprocket, position the film so it can touch the lower sprocket film stripper and accommodate your first finger. After checking the film for proper seating, close the pad roller assembly. Remove any excess film by turning the take-up reel in a clockwise direction. Always cinch down the take-up spindle against the reel. This will prevent a sudden jerk on the film at startup, which could damage the print. You should also cinch the spindle of the upper magazine against the full roll of film in a counterclockwise direction. With the threading of the film accomplished, turn the machine over by hand, listening closely for any tearing or crackling sound that could indicate film path misalignment. Finish the job by closing all the compartment doors. The preparation and operation of the lamp house requires constant vigilance on the part of the projectionist if the desired end results are to be achieved. Lamp preparation begins by inserting both the positive and negative carbons into their respective holders. The positive carbon is held in position by the positive rest and clamp. The clamp assembly can be moved by engaging the release lever. It's a good practice to position the clamp assembly to the furthermost rear of the positive carbon to prevent you from running out of carbon before a given reel ends, causing either a darkened picture or no picture at all. Avoid over-tightening the clamp on the carbon. The burning end of the positive carbon should be positioned beyond the rest about 1 1/8 inches. Setting the positive carbon at this distance from the rest should get you somewhere within the optical axis of the mirror. To position the negative holder, use the center override knob for the negative feed and move the assembly to its furthermost rear position. Insert the negative carbon in the holder by raising the spring-loaded clamp. Position the tip of the negative carbon so that it protrudes beyond the front of the negative guide about 1 inch. Then release the holder. To start the lamp, first make sure that the hand dowser is closed. Turn on the lamp house power supply and momentarily touch the 2 carbons together, then quickly draw them apart to start the arc or burning action of the carbons, positioning both carbons so that they appear on their respective lines on the arc imager card. During projection, constant monitoring of the lamp house operation is required to ensure that the carbons remain in alignment to give the best possible illumination on the screen.
Well, there you have it. The film's been inspected, the equipment serviced and cleaned, and it's ready to go. I'm sure you've realized by now that you're not going to be able to remember everything that you've seen here today. So you may want to view this tape again after you've had more on-the-job experience. Your performance as a projectionist will determine the patron's opinion both of you and of us. It's our combined goal to deliver the best quality product possible. You're the key in reaching that goal. To help, there's a wealth of information and assistance available to you from every level of AAFES management. No matter what the question, no matter how big or small the problem, we're here to help. Asking questions can save you and us considerable time, money, and most importantly, it can ensure the patron's continued confidence in us as a team that is able to deliver the high-quality product and service that they deserve and expect from us.